All right. I'm very happy to introduce Professor Thierry Goudon. We wait for Alexi, maybe. That's very good. All right. I'm very happy to wait for Alexi.
Unintroduced.
Alexi. Oh yeah. So what's happening?
Yeah.
Also, everyone's voice is a little hoarse.
Oh, hey, let's go.
Presque Charbel. All right, so Grandpa's here. All right, I'm very happy to reintroduce Professor Thierry Goudon, who will speak about a well-balanced scheme on staggered grids. Okay, so thank you very much. So the topic of the talk is devoted to numerics, and of course this is a wink to the beginning of our career in Nice with Alexi, because he was doing this kind of stuff when he arrived in Nice, and we were discussing a lot together with under the auspices of Frédéric Poupeau. We benefited a lot of his kind of support, and yes, I'm very happy to give this talk about the continuation of what you did at that time. So the talk is mainly focused on a joint work with Sébastien Mingeot, who is one of my collaborators in University Côte d'Azur, French Riviera University, which is the new name of the University of Nice. People who are not aware of change of the landscape in France. But actually, this is a part of a series of work with different people. So Florent Berthelin, who is also one of the collaborators of Alexi. So this guy is also a Lebanese, so not Carlos Ghosn, it's Charbel Ghosn, actually. I think there is no connection with the family of the former CEO of Renault, Stella Krell and Julie Lobel, who was one of the PhD students. Renault Nissan, sorry. So the motivation is a numerical treatment of hyperbolic equation or conservation laws, but with a right-hand side containing zeroth-order terms. So typically, I have in mind the simulation of gravity terms in Euler equation. So it's a very simple example. So usually you write zero on the right-hand side, but here you want to take into account the gravity, so something which is proportional to the density. And another example is given by the Scholler-Water equation, where you have some description of the bottom of the flow. Okay, so it looks very simple. So the equation is dtu. U is a vector of unknown. It could be a vector depending on the model, plus the space derivative of a certain flux function, and the right-hand side only contains zeroth-order terms. So at first looking, it looks very simple. So you will only say, pay attention to the complicated term, which is a space derivative, where you need to be clever, and right-hand side will be okay anyway. It will work with the name thing that you can think of. But actually, this is not the case, and this observation dates back to Alain-Yves Leroux in a series of work with Patricia Cargo and Jim Greenberg. So everything is summarized in this sentence. So he said, many classical schemes cannot maintain steady solution, or they are achieving them with very poor accuracy. And this is because the scheme is not able to preserve the balance between the source term, the S of U, and the flux term, which is the XL of U, that contains the internal force in the fluid. So this is really a drawback of any classical scheme. And this has given rise to a result stream that we call a well-balanced scheme. So you can look at the book of François Bouchu or Laurent Gosse, for instance, for a very complete presentation of this kind of schemes. So I want here to revisit this issue dealing with staggered grids. So I will do something which is really uncommon, since when you want to discretize this kind of equation, of course, in principle, you colocalize all the unknown of the vector U. So here I want to do something different. I want to store some unknown at some point and other unknown in different points. So typically, I will have some point xj, j plus 1, some interface. And for some reason, I will store, let's say, the density on the temperature and the energy at those points and the velocity at the other points.
Okay, I will explain why it's interesting to do that. Okay, so I want to do this uncommon things to write a numerical scheme for the conservation law and to explain how I will deal with the source term in this framework. So first, I want to do a warm-up, which is something very easy, to explain the philosophy of finite volume schemes. And actually, it's very natural to understand what is a finite volume scheme. We have to go back to the derivation of the equation. So we all start a lecture on the conservation laws with a picture like that. So you have a domain omega. We are saying that we look at the time evolution of some quantity u, the integral of u over this domain omega, and we are saying that this is due, the evolution of this quantity is due by gain and loss at the interface on the boundary of omega with a certain flux. In this way. So now you write that this quantity is exactly the f of u. You use integration by part, and you end up with the equation dtu plus dxf of u equals 0. So I want exactly to reproduce this reasoning at the discrete level. So I integrate the equation over time between Tn and Tn plus 1 and over a certain cell, which is, for instance, delimited by Xj and Xj plus 1 half. And sorry, let me between those 2 points to know what happens for a cell which is centered on Xj. Okay, so this is exactly what I want to do. So I integrate the equation. So first I have the evaluation of u at the different time. And here I have the evaluation at the interface, j plus 1 half, j minus 1 half of the flux. And now the idea is just to mimic this formula to define a scheme. So my numerical unknown will be something which is intended to approximate this mean value. And I have to find a clever definition of the flux at the interface, j minus 1 half, j plus 1 half. And it's quite natural to think that at this interface, I will use the value in the neighboring cell in xj and xj plus 1. Okay, so this is exactly what is explained here. And the consistency property that we impose in the construction of the flux, that if you evaluate the flux function with the same argument, you recover the flux of the continuous function. Okay, so this is all what you need to know about finite volume scheme, and it's very natural, and there is nothing mysterious in this business. So now let me explain the difficulty with the source term with the basic example, which is the example of the Burgers equation. So this is exactly what is in the paper of Alexis about that. So this is the Burgers equation. And in the right-hand side, you have the product of u, the zeroth order term, plus dx of z, and z is something which is given. Okay. And so this equation, you have an equilibrium, so you get rid of the time derivative. So you obtain the equation dx of u squared by 2 equals the first term, minus u dxz. So now you expand the derivative on the left. So you have u dx u. You get rid of u, and you obtain that dx u plus z is 0. So in other words, u plus z should be constant. So this is the definition of the equilibrium state that you want to conserve numerically. So now, okay, you know that you have equilibrium state, but just think of a very naive scheme. As I told you at the beginning, so you write your favorite scheme for the Burgers equation with some definition of the flux function. And for the source term, what would be very natural is to say that there is a space derivative of the z. So I take the centered finite difference for the z, and I multiply by the u at the position xj. Okay, it's very natural to think a scheme in that way. Okay, so for instance, for the flux, for a reason that will be clear in a minute, I'll use the Enquist-Osher scheme. So I take the negative part of uj plus 1, and I take the square. So this is because the situation means that the velocity of propagation goes from right to left. So you are using the information coming from right to approximate what happens at the interface. And here, this is exactly the opposite situation. So this is the the translation of the upwarding principle that guides the conception of numerical schemes. Okay, so this is a very nice scheme which is very tempting to use for solving this equation. And here is what you obtain. So this is a very simple situation with the z which is given by this cosine function. And here, let me start with the equation and the simulation in the bottom. So the equilibrium solution is exactly given by this function in red. And the naive scheme that I gave before produces this curve here in red or in blue. So of course something wrong happens. So here this is a zoom, and you see that there is a discrepancy here between the solution that you expect and the solution that you get. Okay. And this is exactly the situation explained by Alain-Yves law. And not only this is a problem for the long time result, but of course, you see also some differences looking at the transient state. So here you have differences in the solution produced by the different scheme. Okay?
I have a question.
Yeah.
Is this gap scale with mesh width in some predictable?
Yeah, here this is delta x.
Okay. Is that what you'd expect from the?
Yeah, but you have to pay more to obtain something which is reasonable. And again, you are wrong at the end, but you see that you are also wrong in the transient state. Okay. Of course, the error maybe is of size delta x, but this is something that if you are clever, you can avoid this kind of problems. So what does it mean to be clever? So the idea is in a paper by Botchorishvili, Bertam and Alexis. And the idea is to modify the definition of the flux function, the fj plus 1/2, by taking into account what happens in the source term. Okay. So the idea is the following. You have attained the UJs, and you use the equilibrium relation to define something at the interface. You have two quantities, uj plus 1/2 right and uj plus 1/2 left, defined in this way. Okay, so I'm just using the fact that this quantity at equilibrium will be constant, and I modify the scheme by replacing the uj plus 1 by uj plus 1/2 right, and uj minus 1 by uj minus 1/2 left. Okay, and the good news with the strategy is if you look at what happens when you are at equilibrium. So at equilibrium, as I said, this quantity is constant. So it is equal to uj plus zj. So in other words, those new quantities, reconstructed quantity, are the same and they are equal to uj. And if I plug this information in the scheme, I will have the flux function evaluated at fuu, and here the same. So this cancels out, and the u is not modified by the scheme. Is that okay? You recognize your work? Okay, so this is the first remark, that you conserve the equilibrium. The other remark is to say that this modification is consistent with the approximation of the source term. So to observe that, the idea is to say, okay, I have modified the scheme in this way. So I rewrite the usual scheme plus an error term. And the error term is supposed to describe the source term. Okay, so this is exactly this computation. So I have to evaluate this difference, which is supposed to approximate u z prime. And this is indeed what happens. So I did the computation for the Nyquist-Osher fluxes, which is given by this formula. So now you have to integrate the negative part of S between uj plus 1/2 right and uj plus 1. And using the definition of the reconstructed quantity, you indeed realize that you have an approximation at first order of this quantity. Okay, so you not only you preserve the equilibrium, but you have also an approximation that looks reasonable of the source term in this way. Okay. So now the next question is, this is quite complete as far as you are looking at scalar conservation law. What happens when you are looking at systems and systems coming from physics and the Euler equation? So a question of shallow water case. So I will speak right now on the barotropic case. So the pressure is just a power of the density. So shallow water corresponds to the case where the exponent is 2. And I want to solve this equation with zeroth order term, which is rho dxz. And I am particularly interested in equilibrium at rest. That means that the velocity is 0. And I have to solve this equation, dxp equals the source term. So there is a clever way to integrate this equation to obtain a relation, which is more or less the same as before for the Burger's equation. We are just saying that this function of rho plus z is a constant. Okay, and that's exactly the same formula as for the Burger's case. For the shallow water system, this is nothing but E of rho is rho. So we are saying that rho plus z is constant. Okay, you just have to keep that numerically. So now let me explain what happens when we are looking at this difficulty in the context of staggered grids. So this is the part which is not usual. Usually when you solve the earlier equation, you really want to preserve the structure system of the equation. And it's very natural to colocalize the velocity and the density and to have both of them discretized at uj. So I want to do something different. So I have two grids, the ej, where we store the velocity, and the ej plus 1/2, where we store the density. Okay. So the principle is nevertheless the same. That is to say that, sorry, I will explain with Blaslev. Does it work? Okay, I will do that with the mouse.
It's just off. It needs to be turned off.
It's turned off? Okay, I will explain. It's better for that screen too with the mouse, so don't worry. So for the density, what I need to do is to do a mass balance here on this domain, okay, with the interface Ej and Xj plus 1. So if I want to update the density, which is inside the cell, here in the middle, I need to define fluxes F, J plus 1, and Fj. Okay. If now I turn to the equation for the U, I need to integrate the momentum equation on this grid. And now I have to define fluxes, momentum fluxes on the interface J minus 1/2 and J plus 1/2 that I will call J. Okay, and I have also a discretization of the gradient of pressure somewhere. Something which is also a bit mysterious in this passage from the first equation to the second is that I need the rho at this point, but here I will need also the rho on the blue grid, if you wish. Okay, so I need mass fluxes and I need momentum fluxes. What is quite natural, nevertheless, is to take advantage of the fact that at the point Ej, I have naturally the velocity which is stored. And it's very natural to use this velocity to define the mass fluxes. Okay, this is just the intuition that tells you this guidelines. So now I need to spend some time to explain why I need something so complicated and what is the interest of dealing with staggered grids. So the motivation actually comes from either the low Mach number regime, or when you want to adapt the discretization of earlier equation to deal with more complicated model describing multifluid flows. So I will give you an example in a minute. So the typical feature of this kind of flows is the fact that you have the flow is non-homogeneous, so exactly as Raphael did yesterday. You have an equation, but you want to keep something dependent, space dependent for the density. And we have also a constraint on a certain velocity. And typically this constraint is dvu equals something for a certain velocity u. Okay. So as far as you want to do analysis of the equation, you have various formulations of this constraint. But it's not clear that once you have discretized the equation, you preserve the equivalence between all these formulations. And the goal of dealing with staggered grids is to have a framework where it is easier to preserve the equivalence between the different formulations of the equations. Another motivation for this kind of complicated framework is the fact that if you colocalize all the unknown, For the pressure, when you have a constraint, you know, if you think of the incompressible Navier-Stokes equation, a way to have an equation for the pressure is to take the divergence of the momentum equation, and you obtain the relation looking at Laplacian of the pressure equals something. Okay, and this is a way to define the pressure, and this is what you use numerically. If you do that, colocalizing the ordinary known, this is a remark that goes back to Arlo and Welch, actually, who invited the Mach schemes. If you do that, colocalizing ordinary known, typically you discretize the Laplacian with this kind of formula, where you see that you are uncoupling the odd and even terms. Okay, so you are creating some spurious modes that do not appear in the continuous equation, and this is a source of instability of spurious oscillation that you want to get rid of. Okay, so this is why there is some advantage, conceptual advantage in dealing with staggered grids. So just to give you the motivation coming from multifluid flows. So here, this is the kind of model I'm interested in. So maybe do not look at all the details of the equation. Just keep in mind that you have two species, a species of particles and a carrying fluid, if you wish. So for one of the species, the density is phi, velocity is v, and for the other one, the density is n, and velocity is u. Okay? And you have some coupling between the two, and the coupling arises from friction forces, which are given by this difference, u minus v. And there is also somewhere in the equation a common pressure P, common pressure field P. And this common pressure P, as I told you, comes from a constraint. So actually, the phi and the n are not mass density in this framework. They are instead volume fraction. And the sum of the two volume fraction is 1. Okay, so at some location, you have either you have a mixture of dispersed phase and the carrying phase, but the sum of the two is always 1. So a consequence of this constraint is the fact that if you add the two mass conservation equations, so this equation for phi, the equation for n, you end up by saying that the mean velocity, mean volume velocity, phi of v plus n of u, is divergence free. Okay, so this could be seen as a definition of the Lagrange multiplier associated to this constraint, which is the P. And you can perform exactly the same kind of computation you are used to with the usual Navier-Stokes equation. You take the divergence of the momentum equation and you obtain an equation for more or less the Laplacian of P. But then numerically, you go back to the difficulty explained before to uncoupling the odd and even points. Okay, so this is the motivation of this series of work. Okay, so let me go back to this picture. So just to rephrase what I said before. So for the mass equation, you make a mass balance in the red cell here between xj and xj plus 1. So you need to define fluxes at this point and this point on the left. And for the velocity, you will do a momentum balance in the blue cell, and you need a momentum flux at this point, xj plus 1/2 and xj minus 1/2. Okay. And of course, for the mass flux, it will be naturally a function of the velocity that is stored at this interface. And you need to decide how it depends on the density in the neighboring cells. Okay. And for that, you will use some upwinding principle saying that some velocity goes from left to right, from right to left. For the momentum fluxes, we will see that it will be a bit tricky. And the idea is to say that rho u square is u times rho u. So you will apply the u depending on the side of certain flux rho u, which is exactly the mass flux. So you will use the mass flux to define the momentum flux. Okay. So now I need to define more in detail the typical form of the fluxes I will use, of the mass fluxes that I will use. And the idea again is to go back to a kinetic framework. So actually, this is an idea that goes back to Jan Brenier, transport, how do you say it in English? Sorry? Transport collapse framework. So the idea is to design a scheme inspired by the fact that the Euler equation comes in some sense from a kinetic derivation, where you have BGK or Boltzmann equation hidden behind. And you use this idea to define relevant fluxes. And actually, the Enquist-Osher scheme that I gave at the very beginning for the Burgers equation can be derived in this way. So if you know a little bit about kinetic schemes, sometimes it's a bit complicated because, as I told you, there is you go back to some kinetic framework behind, and the fluxes are usually defined by some complicated integral with respect to an auxiliary variable psi. And the computation of this integral could be costly numerically. So here, this computational cost is completely hidden because I have an explicit formula, which is very simple. So in some sense, you completely forget this complicated derivation. So you have two functions, f plus and f minus. So f plus means that the velocity goes from left to right, and f minus tells you that velocity goes from right to left. And it tells you how to upwind. Okay, so this explains the fact that the f plus uses j minus 1/2 as the density, and the f minus uses j plus 1/2. And this is a formula that I get for the f plus and f minus. Okay, so this is a variation around rho u. Okay, I will give you a picture in the next slide. So the idea to obtain this flux is to say that the f plus and f minus are the integral of a certain Maxwellian state times a certain velocity variable psi when psi is positive and when psi is negative. So this goes back to an idea by Kaniel, and I used to obtain the formula before this definition of the Maxwellian state. Okay, so this is a characteristic function of rho divided by 2c of rho. C is the sound speed, and I use a psi which are enclosed between the two characteristic speeds of the equation. Okay, so I remind you, sorry, I was a bit fast. The characteristic speed of the barotropical Euler equation are u plus minus c, where c is the square root of p prime. Okay, so this is a way to keep track of the fact that you have some characteristic of the equation that governs the way to upwind the fluxes. And there is another definition which is quite tempting to use, is to replace this Maxwellian function just by the Dirac mass when c equal u, which is a material velocity. And I will comment a little bit more on this particular shots. So here is a picture that I promised. So this is the picture. This is u, and this is the f in the here, and the upwind scheme would be just a straight line. So we are just smoothing a little bit the straight line by using this fancy definition. And I will explain why it is interesting to have this smoothing up. Okay. So the key property for the analysis of the scheme are the fact that you have some symmetry property when you change the sign of u and the change of the flux. And of course, you can also check that you have the consistency of the flux if you have the f plus and the f minus evaluated with the same arguments, you get rho u, which is what you expected. Okay, so this is for the mass flux. We are able to find a relevant definition of the mass flux. So now let me switch to the momentum flux. So now I need to take the momentum balance over the cell centered at Ej, and I need to define momentum fluxes at the interface j plus 1/2, j minus 1/2. And the idea to this end is to use the mass fluxes because the momentum flux is rho u times u. So I use this definition. First of all, I remind that I have mass fluxes in the interface j and j plus 1. From these mass fluxes, I define a new mass fluxes at j plus 1/2. So there are many ways to do that. So the way that we choose is to say that f plus j plus 1/2 is the average of the positive flux at j and j plus 1. And f minus j plus 1/2 is the average of the f minus of at the two other interface. Okay. There are other ways to do the same kind of average. Maybe you can interpolate the plus and minus and and the average, it gives something different, but we prefer this one. For the gradient of pressure, it's easier because I want to define something that approximates the gradient of pressure at xj, but I have density at the interface. So the pressure is naturally centered in this way. Okay. So something else which is a bit tricky in this business is, sorry, let me go back. As I told you, to update the velocity, I need to define a new density on the cell centered at xj. And the natural way to do that is to take the average on the cell xj between ρj plus 1/2 and ρj minus 1/2. And here there's something which is remarkable. This is a consistency property of the staggered scheme. Is the fact that if I project on the blue grid the mass conservation equation, I still obtain the mass conservation equation with this definition of the fluxes. Okay, so you have a density on the two grids, and the two densities, the two discrete densities, satisfy a discrete conservation equation. Okay, so here just let me summarize the kind of results that we have been able to obtain. I will go back to the source term later on. So first of all, something which is very important is to understand the stability of the scheme. So stability of the scheme here is in the sense that we preserve the positivity of the density, and you obtain a stability condition, CFL-like condition, which looks like the usual one. Okay. So depending on the characteristic of the equation, you have a constraint on delta x and delta t. Something which is a bit boring is to do the consistency analysis. So you have a Leibniz-Doroth schemes, which is that if you have the good hypothesis, then you converge to a weak solution of the equation. Something which is maybe more important is to say that for the barotropic case, at least, we have an entropy selection criterion, and indeed the scheme is entropy decaying. So here it's a bit harder for the analysis because we have two grids, and you have to combine quantity on the two grids. Okay, so going back to numerics, I explained you that there is this choice of the Maxwellian state to define the fluxes, and it could be tempting to work with the material density, just saying that the Maxwellian is the Dirac mass centered at U. Actually, this is a scheme that has been introduced by Herbin and Larcher, but there is some advantage in dealing with the regularized flux function, and this is explained in this picture. So this is a simulation with on the bottom the scheme with the Dirac mass, and on the top the scheme with the Maxwellian state. Okay, so here the scheme is defined with just the material velocity. On the top, it is defined by taking into account the characteristic field of the equation. And what you see is that the scheme centered on the material velocity, there are some oscillation when the velocity is 0. Okay, so Herbin and Larcher are able to get rid of this oscillation by introducing by hand by tuning some numerical diffusion, and our scheme does it by itself. Okay, so this is the advantage of the regularized flux that we use. Okay, I will explain at the end of the talk how to adapt the strategy for the full Euler equation and how we obtain a local conservation for the energy. Everything can be adapted to deal with second order by using muscle-like procedure. It can be done for multidimensional equation and even working with unstructured grids. So this is another business, and I don't want to enter into those details. And as I told you, it can be adapted to the simulation of mixture flows and low Mach regions. Okay, so now let me go back to the purpose of the talk, is how to insert the treatment of the source term in the momentum equation. Okay, so the source term, the naive way to discretize the source terms is to say that the derivative of the z is just centered and multiplied by ρj. And this produces the same difficulty as for the Berger's equation. We have something which does not preserve the equilibrium solution. Okay, so there is an exception that I will detail in a minute. So just to make a break, a very fancy simulation, kaleidoscopic-like simulation. So you have 3 columns of water, and you left the 3 columns falling, and you obtain this kind of a very nice picture. So on the left, this is the first order scheme. On the right, this is a second order version. So of course, you will see that it is much more precise, but it's kind of relaxing, right? It's a bit of color in the talk. Okay. Sorry?
What is represented as the density?
It's a density. So here, this is what you obtain at the end. So of course, you see that all the structures are are better represented with the muscle scheme than with the first order scheme. Okay, so nevertheless, the naive scheme that I gave in the previous slide does not preserve the equilibrium state. So for the shallow water equation, the equilibrium is density plus the topography equal constant. So at rest, the velocity is 0. So the mass flux is given by this formula. So this is the F plus velocity 0, the F minus velocity 0. I use the formula and I obtain this quantity where the Tj is the soon speed. By using the equilibrium relation, I can replace this difference between the rho by the difference between the z. But it is quite clear that this formula does not cancel out. This is the flux at fj plus 1, just fj plus 1. It does not cancel out with the fj. So we do not preserve the equilibrium with the scheme. So you need to do something better. And the idea is to incorporate the source term in the definition of the mass flux. So to do that, we use a trick by Odius, essentially, with many papers with different collaborators, so Bristow, Bouchu, Klein, Pertal. So the idea is the following. So the quantity which is conserved is E of rho plus Z. So I use this formula. First, there is the maximum between the Zj plus 1/2, Zj minus 1/2. I use that difference. I add the E, and I take the positive part. So this is quite important because you want to use this formula to reconstruct the density, and the density is naturally non-negative. And this trick preserves the non-negativity of the density. Okay. So with this formula, what you do, I remind you that you do the mass balance in the cell centered at Tj plus 1/2, and you define some quantity, some new density at the interface, some density on the left of the interface, and another on the right of the interface by using this base formulas. And the key point of the definition is the fact that if you are at equilibrium, the interface quantity are exactly the same, so that when you replace in the definition of the scheme, now you do not change the density. If you are at equilibrium, with the mass equation, you do not change the equilibrium. So what happens with the momentum? So in the momentum, we follow exactly the strategy as before. We replace the density, the appointed density by the reconstructed quantity at the interface, the rho left and the rho right. And for the gradient of pressure, we do exactly the same. We use the pressure at the interface. So in other words, of course, for the convection fluxes, if U is at rest, if U is 0, it gives 0. So that's good. So the question is now, how do we recover from the gradient of pressure? How do we recover the source term? So to see that, we replace the gradient that we impose with the usual one, and then the source term should be approximated by this difference. Okay. So again, as I told you, if you are at equilibrium, we remark that you do not change the equilibrium. Okay, so to understand what happens, whether or not we are consistent with the source term, it's quite interesting to spend some time on the shallow water equation because the computation is very easy, because everything relies on the remarkable identity. A square minus b square is the product a minus b, a plus b. Okay, so this is what I want to explain. So here you have the source term that I can rewrite by using this identity. Okay, so I have to compute this Sj, which is intended to approximate minus rho dz. Okay, so I use now the formula for the reconstructed quantity. So rho right is rho minus the negative part of the delta z, and rho left is the same with switched from on j plus minus 1/2. Okay, so now I use that definition to replace this difference here, and I obtain this formula. Also, I have replaced rho right minus rho j plus 1/2 by the delta z. Okay, and the same for the other guy. Now I reorganize the terms so that I make appear the average between rho j plus 1/2 and rho j minus 1/2. Okay, so I make some mistake here, so I reintroduce the terms, and now I'm looking carefully at this formula. And what happens if I reorganize the term in the last line? I make appear this quantity, and now I have the product of delta z plus delta z minus, which is 0. So this is the good news in this computation. And at the end of the day, what you get is that the discrete source term is precisely the average between the density on j plus 1/2, j minus 1/2, times the delta z. So this is an approximation of rho dz, plus something which is of higher order with respect to the discretization, the size of the mesh. Okay. So this goes away as delta x goes to 0. So the scheme is indeed consistent with the source term. So in the general case, we have more or less the same computation. It's a bit more tedious because you need to do some Taylor expansion. But anyway, what you obtain is something of the same flavor. So the source approximates rho dxz plus some error term. Okay, so now just let me spend a minute on another scheme proposed by Doyen and Goudon, which is very simple, so surprisingly simple, working on staggered grids. So the idea is precisely to use this variation of the scheme where you use, for the definition of the mass flux, the material velocity. So in other words, what you get for dating the density is these differences of flux, where you have just, for instance, here, when j plus 1 here is positive, you are using the density coming from uj plus 1/2, and when this velocity is negative, you are using rho j plus 3/2. Okay, so this is very natural to discretize in this way. For the momentum equation, we have more or less the same kind of trick, and for the pressure gradient, you use a central difference, which is quite natural, and we use something which is very naive and very natural also for the source term. Okay, so you have the average of the rows and the central difference for the z. And the scheme, which is very simple, is well balanced, because if u is 0, you get rid of everything, and the two last terms here recombine precisely in this way. And if you are at equilibrium, precisely this quantity is a constant, so this one equals this one, and you obtain 0. Okay, so the scheme is well balanced, but there is a trick here which is highly dependent on the specific form of the flux and the specific form of the pressure law. If I change the pressure law, it does not work. Okay, so here I used at some point the remarkable identity on a square minus b square. Okay, so it doesn't work for any pressure law. Okay, so now let me explain how I construct a second order version of the scheme. So the strategy, the main difficulty is to do things in the right order. So you define quantities by using P1 interpolation. So to this end, you need some appropriate slope, and you limit the slope because you want to avoid some oscillation next to discontinuities. Okay, so this is something which is very standard. And the quantity that you reconstruct in this way are the density and the conserved quantity at equilibrium, which is E of rho plus Z. From that, you define some auxiliary topography. And the thing which is a bit mysterious here in this business is the fact that now the reconstructed topography depends on time, because it depends on time through this quantity. So you need to reconstruct this quantity at each time step. And once you have these interpolated quantities, you use the same trick to define interface density preserving the equilibrium by the same formula as before. And now you replace in the mass fluxes the usual density by the density obtained in this way by the muscle plus reconstructed procedure. Okay, up to now there is no surprise in this construction. So you do the same for the momentum flux, and for the pressure you do more or less the same, but now you just keep the usual definition P rho G plus 1 half. For the source term here is the part which is a bit tricky. The first idea is to say, okay, I replace the rho by reconstructed quantities. So I replace everywhere in my scheme the rho right and left by the muscle quantities. This idea does not work because if you do that, you have two reconstructions of the density at the same interface, and you produce naturally an error over the delta x. Okay. So the idea is actually simpler than that. You only use the reconstructed quantity from the first order scheme, but you remove the quantity in the consistency analysis that remains of first order. So let me go back. It's better to use the present formula. When I did the analysis for the shallow water equation, I obtained this expression for the approximated discretized source term. The first term is okay. That's exactly what you want. And there's a second order approximation of rho Z prime. That kills you is the other guy that remains first order. And it's here whatever you want to do. So the idea is just to remove this guy that bothers you. Okay. And this is the same situation in the linear case. And this is exactly what Dunawan and Doyen did. They just approximate naively the source term, and they obtain something which is naturally second order. So here is a bit surprising that you need to do something different on the source term to reach a second order accuracy. Okay, so here is a few simulations to explain how it works. So this is a quite standard test case for the lake at rest. So you have the formula for the topography. You have a reference simulation here in black, and you see the difference between the first order scheme and the second order scheme with the same delta x. I will explain the interest of working with second order accuracy. So here, this is another classical test case. So in principle, people cut the picture, just cutting at this location and this one, and just focusing on what happens here. And so here we are doing as well as the competitors in the sense that you reproduce quite well the structure. It is interesting is also to discuss what happens here on the right and on the left. And this is not a mistake of the scheme, because actually we compare the result of the scheme with an asymptotic solution, which is supposed to be exact, but asymptotically. Okay. So of course, for transient state, there is no reason to stick to this reference state. And indeed, this is what you can see if I continue the simulation for larger time and on a larger domain. You see that the difference between the simulation and the reference scheme tends to 0. Okay. So this is when we are speaking about exact solution, it has to be taken with some caution, okay, on the meaning of reference solution. Okay, so here this is another test case in 2D. So the topography is a paraboloid. Okay. And we have an explicit solution, which is time periodic, and the interface remains completely flat. And what is a bit hard in the simulation is a wet-dry transition when you are moving the interface. Okay, it goes back and forth on the bottom of the ball, if you wish. Okay, so here you compare a cut line of the free surface. So of course you see that the second order scheme does better. And here this is a comparison with the exact solution. Again, the second order scheme does better. So you have a few minutes left. Okay, so just to explain how to adapt for the full Euler system. So here just rewrite the full Euler system that you are used to with the full energy, capital E, which is a combination of kinetic energy plus the internal energy. And the internal energy is used to define the pressure by some pressure. Okay. So of course there is a difficulty when you work with staggered grids because the velocity and the density are not at the same location, and the internal energy is naturally located at the same place as the density, and so there is some ambiguity for the total energy. Where do you store the total energy? So to do that, you get rid of the total energy, and you work with the internal energies, which satisfy this equation. So here you should be shocked by this formula, because it's okay as far as the solution is smooth. So you need to do something when you have shocks, of course. But anyway, this is an idea which has been used also by Hermann, Lache, and others. And the idea is the following. So I will be a bit fast for the mass equation, momentum equation, for which the idea is exactly the same as before. What I need to explain is what happens for the internal energy equation. For the internal energy equation, for the fluxes, it's not a big deal because this is rho u times E. So I use the mass flux times the upwinding of the internal energy. And the trick now is to insert a source term that accounts the fact that the internal energy equation comes from a balance of energy, and you need to take into account what comes from the discrete equation for the kinetic energy. So this is the formula which is explained here for the right-hand side of this equation. Okay. So for people working with staggered grids, this is the way to cure what happens when you have discontinuities. So what is a bit difficult is to perform the analysis for the stability condition to preserve the positivity of density and internal energy. So you have some mysterious relation between delta t and delta x, but that looks like what we are used to. What is much more difficult is to recover in this way a conservation of the total energy. And usually people obtain conservation of total energy when you average between the whole scheme. So here we have been able to obtain a local version of the conservation of energy by defining some average, because you need to recombine everything on the same grid. So we have some average total energy. And this quantity indeed satisfies a local version of the total energy conservation. Okay, so now the last part is to insert in this business a treatment of the source term. So you have a source term for the force and in the total energy equation. And to this end, we are using an idea coming from Capelli and Mishra, which is to impose not only the mechanical equilibrium, but also thermical equilibrium by imposing the form of the internal energy at equilibrium. Okay, so you have some fancy formula. So since time is over, I'll just finish with a simulation. So here the idea is to show the ability of the scheme to capture the equilibrium just with a small perturbation. So you have the equilibrium, you have a small perturbation, which is time periodic on the left, and you want to see what the scheme does. So on the top, this is a simulation of Mishra and Capelli with different scheme. And of course, the blue curve is with a non-well balanced scheme. And you see that you have some errors. So the scheme is not able to catch the equilibrium state. And on the bottom, This is a result that we obtained 2 days ago, actually, a bit in a rush for that, with our scheme. Okay, so thank you for your attention.